When you look at the sheer scale of modern AI training today, I mean, we're talking about resource needs that are just astronomical. Tens, even hundreds of yottaflops.
Yeah, it's hard to even wrap your head around that number. It's like hundreds of times the planet's estimated compute power just a couple of years ago.
Exactly.
Yeah.
Which means efficiency isn't just, a nice to have. It's the absolute bottleneck for building the next big thing in large language models.
Precisely. And the industry's kind of settled on 8-bit floating point, FP8, for accelerating training now. But the push, mathematically and practically, is towards 4-bit FP4.
Right.
The sources we're looking at basically confirm this is the next logical step, and the potential payoff, it's huge. We're looking at maybe 2, even 3 times the speed and cutting memory use in half compared to FP8.
But that drop to 4 bits, that's where things usually fall apart, right? Stability, convergence, accuracy, they all take a hit.
Historically, yes. That's why this NVIDIA work is so interesting. They've got this new NVFP4 format, but more importantly, a whole methodology built around it.
And they didn't just theorize, they actually did it. Trained a huge 12 billion parameter model on, get this, 10 trillion tokens. That's really the first solid proof we've seen of stable, accurate 4-bit training at that kind of multi-trillion token scale. Okay, let's unpack this, starting right at the beginning. Why is training with only 4 bits of precision just so darn difficult?
Well, the core difficulty, it really boils down to quantization. When you shrink the precision down to just 4 bits, you severely limit 2 key things.
Okay.
First, the dynamic range, that's the gap between the smallest and largest numbers you can represent. And second, just the sheer number of unique values you can actually encode.
So it's a much coarser representation.
Much coarser. And that immediately challenges stability. It makes convergence really fragile, and you need extremely careful implementation, especially for these giant models trained on these massive data sets.
Let's maybe define that tiny structure a bit more. You mentioned microscaling formats, MX formats like MXFP4. What does that actually look like in terms of bits?
Right, so MXFP4 typically uses what's called an E2M1 representation. That's 1 bit for the sign, plus or minus, then just 2 bits for the exponent that sets the scale, and only 1 bit for the mantissa, the significant digits.
1 bit for the mantissa. That sounds incredibly restrictive.
It is. It means you basically only have 8 possible non-zero positive values you can represent. Something like plus or minus 0, half, 1, 2, 3, 4, 6. That's it.
Wow.
Think of it like trying to paint a photorealistic portrait, but you're only allowed 8 specific paint colors. Red, blue, green, maybe a few shades. You just can't capture all the subtle tones.
So any value in your model's tensors that doesn't perfectly match one of those few points has to be rounded pretty aggressively.
Exactly. Aggressively rounded or scaled. And that makes the whole network hypersensitive to outliers, to any values that fall outside that very narrow range. What's fascinating here is the hardware is actually keeping pace. This whole push is underpinned by the silicon. NVIDIA's Blackwell tensor cores, for instance, they have native support for these narrow formats MXFP8, MXFP4, and crucially, this new NVFP4.
So the hardware's ready to go faster.
The hardware's ready. It can do the math that quickly, but it's useless if the software, the algorithms, the methodology can't maintain numerical stability. That's the bottleneck.
Okay, so given that standard MXFP4 has these limitations, NVFP4 must have some design improvements to tackle that instability.
Yeah.
How did NVIDIA engineer it to squeeze more accuracy out of those 4 bits?
They made 2 key architectural changes to better handle that dynamic range problem we talked about. First, they shrunk the block size.
Block size. What does that mean in this context?
So when you quantize, you often calculate a scaling factor for a chunk or block of numbers to try and fit them into the limited range. Standard MXFP4 does this over a block of 32 consecutive numbers.
Okay.
NVFP4 uses a smaller microblock of just 16 elements.
And why does smaller help?
Because it lets the scaling factor adapt more closely to the local variations in the data. It's like zooming in. You get a more precise scaling factor for that smaller group of numbers, fitting them better into the 4-bit range.
Got it. So it's less of a blunt instrument, more fine-grained. What was the second change?
The second big one is a 2-level scaling strategy, and specifically how they calculate the scale factor. MXFP4 typically uses a scale factor that's restricted to powers of 2. It's simple, it's fast, but it's not very precise.
How so?
Well, imagine the largest value in your block is, say, 5.5. If your scale factor has to be a power of 2, like 4 or 8, you're often forced to round up to 8 to avoid clipping that 5.5 value.
Right, because 4 isn't big enough.
Exactly. But by choosing 8, you're now wasting the upper end of your FP4 range. Those PM44 and PM66 values in FP4 might not even get used, effectively shrinking your already tiny palette of representable numbers.
Ah, I see. So the NVFP4 solution must allow for more flexible scaling factors.
Precisely. It uses a much more precise E4M3 format for the local block scale factor. This E4M3 scale factor is stored in FP8, and crucially, it has mantissa bits, allowing for fractional precision. It avoids that crude power of 2 rounding.
B4M3, so 4 exponent, 3 mantissa. More precision there.
Right. But E4M3 itself has a limited range, so they add a second level, a full FP32 scale factor applied at the overall tensor level. This handles the really big picture range.
Okay, so 2 layers of scaling. Fine-grained local scaling with E4M3, and broader tensor-level scaling with FP32.
Exactly, and the result is that the maximum value within each little micro block gets mapped much more accurately to the maximum representable FP4 value. You utilize the FP4 samples better, and crucially, you quantize fewer of those small, non-zero values down to 0 incorrectly. That better design is key for the improved training convergence they saw.
It's really incredible the amount of mathematical engineering needed just to make 4 bits work reliably. But as you mentioned, the sources are clear. Even this smarter NVFP4 format wasn't enough on its own. They said the training diverged without the full methodology.
That's right. The format helped, but it took this comprehensive 4-part strategy to actually train that 12B model for the full 10 trillion tokens. They call them the 4 pillars of stability.
Okay, let's break those down. What's pillar number 1?
The first pillar is selective high-precision layers. Basically, it's a targeted mixed precision approach. Most of the heavy lifting, the matrix multiplications, GMMs, happens in FP4. But certain layers that are known to be numerically sensitive have to be kept in a higher precision, like BF16 or maybe MXFP8.
And what happens if you try to force those sensitive layers into FP4 anyway?
The training just blows up. It diverges. They found specifically the last few linear layers in the network were extremely sensitive.
Near the output.
Yeah. Quantizing those caused huge errors in the weight gradients, and the whole training run just went off the rails, usually within billions of tokens.
So how much of the network did they have to keep in higher precision?
For this 12B model, it was about 16% of the linear layers, specifically the layers in the very first 2 transformer blocks and the final 8 blocks. They kept those in BF16.
So it's a trade-off then. You give up a bit of the potential FP4 speed-up in those 16% of layers to make sure the whole thing actually converges.
Exactly. You sacrifice 16% of the maximum speed up for 100% stability. Pillar number 2 is the random Hadamard transform, or RHT.
Okay, Hadamard transform.
Yeah.
Sounds complex. What's that doing?
Remember how we said narrow precision hates outliers?
Yeah.
RHT is basically a clever mathematical trick, an orthogonal rotation that they apply specifically to the inputs of the weight gradient calculations, the W grad GMs.
A rotation. How does that help?
Think of it like shuffling a deck of cards where all the high cards are clumped together. The RHT effectively shuffles the data, spreading out those large magnitude outliers. It pushes the distribution of the data closer to a nice, manageable Gaussian shape.
Making it easier to represent accurately in the limited FP4 range.
Precisely. Makes it more quantization friendly.
And they only apply this to the weight gradient inputs, the W grad, not everywhere.
Correct. They actually tested applying it more broadly to the forward pass activations or the activation gradients, but found it didn't help there. In fact, sometimes it even hurt performance slightly, probably by amplifying other types of errors.
Interesting.
So yeah, RHT was only beneficial for via grad inputs. They used a relatively small transform matrix size, finding it hit a good balance between accuracy improvement and computational cost.
Okay, pillar 3.
Pillar 3 is two-dimensional, 2D block scaling, and this one is applied only to the weight tensors. This tackles a really subtle but critical issue that arises during the backward pass, something they call a chain rule violation.
A chain rule violation. That sounds bad, like fundamental calculus breaking down.
It kind of is in a practical sense. It happens because of matrix transposition. When you calculate the weight gradients, W grad, the math requires you to transpose the weight matrix compared to how it was used in the forward pass, WF prop.
Yeah, it's standard backpropagation.
But remember, the scaling factor is calculated along the dot product dimension. When you transpose the weights, that dimension changes. So the weights can end up being quantized differently in the forward pass versus the backward pass.
So you have W quantized one way and W quantized slightly differently, even though they should represent the same underlying weights?
Exactly. And if those quantized representations don't match, the network is essentially calculating gradients for a function that isn't quite the one it just computed in the forward pass. That breaks the consistency needed for the chain rule to hold properly during gradient descent.
Okay, that makes sense. So how does 2D scaling fix this?
Instead of scaling along just one dimension, like a 1 by 16 block, they scale the weights using a 16 by 16 block. It's a two-dimensional grouping. This ensures that the quantization and scaling are consistent regardless of whether the weight matrix is used in its original or transposed form.
So the weights always get the same quantized value forward or backward.
Correct. It eliminates that inconsistency and leads to a smoother, more stable training loss. Interestingly, they still use the finer 1D scaling, 1 by 16 blocks, for activations and gradients, because those benefit more from that finer local granularity and don't suffer from the transposition issue in the same way.
Clever. Okay, that brings us to the fourth and final pillar.
Pillar 4 is stochastic rounding, or SR. Standard rounding methods, like rounding to the nearest even number, are deterministic. They always round the same way.
Yeah, seems predictable.
Which is normally fine, but it introduces a systematic bias, especially when you're dealing with lots of small numbers, like in gradient tensors. Values consistently get rounded down, or tiny values consistently get rounded to 0. This bias accumulates over millions of updates.
Why is that particularly bad for gradients?
Well, gradients often contain many values that are very small but still non-zero. If you always round deterministically, a lot of small positive gradient values might systematically get rounded down to 0, effectively introducing a persistent negative bias into your weight updates. It slows down or even stalls learning.
Okay, so stochastic rounding avoids this bias.
Yes. Instead of always rounding the same way, it rounds probabilistically. If a value falls exactly between two representable FP4 numbers, it has a random chance of rounding up or rounding down. Over many calculations, this randomness cancels out the systematic bias.
Makes sense. Did they use stochastic rounding everywhere? Activations, weights, gradients?
No, and this is another crucial finding. Their ablation studies where they tested removing each component showed SR is absolutely essential for convergence. The training failed without it. But it should only be applied to the gradients, both dgrad and nullgrad.
Only gradients. Why not activations or weights?
Because applying it there was actually harmful. Introducing that randomness into the activations or weights themselves amplified the underlying quantization error and made the whole system unstable again. So SR for gradients only.
Wow. Okay, so it's this intricate combination, the NVFP4 format itself, plus selective high precision, plus the RHT shuffle for wgrad, plus 2D scaling for weights, plus stochastic rounding just for gradients. That's quite a recipe.
It really is. And it's clearly what finally cracked the 4-bit training problem at scale.
Right. So let's get to the payoff. Did it actually work? How did the final 12B model trained in NVFP4 compare to the industry standard FP8?
The results look really good. They trained it for that massive 10 trillion tokens, and the validation loss curve for the NVFP4 model very closely tracked the FP8 baseline curve throughout the entire run.
How close?
For most of the training, the relative error between the two loss curves stayed below 1%. That's basically indistinguishable for practical purposes.
Okay, loss is one thing, but the real test is downstream performance, right? Did the model actually learn useful things, or did the low precision compromise its abilities?
That's the crucial question, and the results here are arguably even more impressive.
Yeah.
They tested it on benchmarks like MMLU Pro, which measures understanding across a wide range of topics. The NVFP4 model scored 62.58% accuracy on the 5-shot test.
And the FP8 baseline?
The FP8 baseline scored 62.62%.
That's virtually identical, a difference of 0.04%.
Pretty much a perfect match across reasoning, math, common sense tasks. It seems like they didn't sacrifice real-world utility for that speed up.
Here's where it gets really interesting. I did see a note in the material, though. While most tasks matched, there was a slight dip, specifically in coding tasks. Any idea why coding might be more sensitive?
That's a good observation. It's likely because coding and some complex mathematical reasoning tasks often depend on very precise, structured information. Think about things like off-by-1 errors, variable names, specific numerical values, indentation, tiny changes can have big semantic consequences.
Right, unlike maybe common sense reasoning, where there's more fuzziness.
Exactly.
Yeah.
So even though the overall loss is matched, that extreme narrowness of FP4 might introduce just enough numerical noise to slightly affect performance on tasks that are highly sensitive to that kind of discrete high-entropy information. But honestly, even with that small caveat for coding, the overall achievement is still remarkable.
Absolutely. And just looking purely at training efficiency, how much better did the NVFP4 format design perform compared to the standard MXFP4 using this methodology?
They did a direct comparison on a slightly smaller 8B model. The results were pretty stark. To reach the same final training loss, the model using standard MXFP4 needed 36% more tokens.
36%. Wow.
Yeah, it needed 1.36 trillion tokens compared to just 1 trillion tokens for the NVFP4 setup. That really highlights how those architectural tweaks in NVFP4, the smaller block size, the better scaling, directly translate into faster, more efficient convergence. Saves a huge amount of compute time.
And they even threw in a practical tip for getting the absolute best final model quality. Yeah, a nice little trick for production. They suggest that if you want to squeeze out that last tiny fraction of a percent of quality, you can actually switch the training from NVFP4 back to a higher precision, like BF16, just before the final learning rate decay kicks in, very late in the training run.
Ah, so you do the vast majority of the computationally heavy lifting super efficiently in FT4. Right, like 99% of the training. And then just polish the final model state in high precision for that last little bit. It closes that tiny potential loss gap that might emerge right at the very end, ensuring the final deployed model is truly indistinguishable from one trained entirely in BF16.
That's really pragmatic. Okay, so wrapping this up, it seems clear that 4-bit training isn't just a theoretical possibility anymore. Thanks to this combination of the NVFP4 format and that sophisticated 4-pillar methodology, RHT, 2D scaling, SR, mixed precision, it's now a demonstrated reality at massive scale. That's a huge leap.
It really is. So what does this all mean? Well, fundamentally, we now have solid proof of concept for the next big jump in training efficiency for these frontier models. It moves the needle significantly.
But it's not quite the final frontier yet, is it?
No, not quite. The current method still relies on keeping that 16% of linear layers in higher precision. And critically, it doesn't yet quantize everything. Key components like the attention mechanism calculations and the communication between GPUs are likely still running in higher precision. So the immediate challenge, the next research frontier, isn't just let's train even bigger models with this. It's refining the methodology. Can they get rid of that remaining 16%? Can they figure out how to apply these 4-bit techniques, maybe modified to the attention layers, to the network communication, to every single part of the transformer?
Fully quantizing the entire model end-to-end in 4-bit without hurting convergence.
Exactly. If they can achieve that, well, what further, almost unimaginable speed-ups in memory savings would that unlock? What scale of model could you potentially train or even run for inference on existing hardware? That's the really exciting question this work opens up. That's the next efficiency frontier.